please take a seat. We're going to start so we don't get too late.
You don't need a microphone. No, I know, but for questions later.
You guys need a microphone.
Yeah, I know.
It's like getting people out of floods or getting some hot stuff from water.
I was getting a nice little workout there. There's a lot of walking around. That's my exercise for the day.
All right, so I'm gonna give you a concise version because I think there's two options coming up. There's a long talk from me, or there's beers at the sink. And I was just telling James, let's do the long talk. We'll do the medium talk and say it's getting late.
You know, since your talk is many tasks,
Yeah.
maybe we could combine the two.
Yes. So
Since we lost that.
you could, I put the talk on GitHub if you want to follow along or just reference it later. So the title's many task computing, and I guess I came to see you about a year and a half ago, and my background in computational science is I was actually a computer scientist in grad school, and then didn't get into computational science until I took a postdoc with NREL, where I was an optimization specialist, and they needed somebody to optimize in parallel. So my background was really traditional HPC, meaning MPI, CVC++, and I didn't really do any OpenMP until I got to CU. So many task computing is kind of a term that probably many of you have heard of, because we actually just stumbled upon it. It seemed like the right fit. There's a lot of things you can call this. So I'll kind of describe that in the first section. I talk about a little bit about high performance computing, and then really define many tasks. And the second part is talking about Python for HPC. How many people like or use Python? Yeah. Oh, good. Okay. How many people are like medium to expert in Python? Okay. So I'll talk about some key packages. You've probably heard of them, but I just wanted to list them out so you have them if you want to look back at it. And then I was thinking a lot about abstraction and why Python is sort of gaining popularity for HPC. And I think it's because it abstracts a lot of the details, and you don't have to learn the nitty-gritty pieces of these computational packages you want to use to really still have decent performance. And then I'll show some stuff that Thomas and I have been working on with just pushing the packages a little bit on the supercomputer to see where they and how far they can go and where we can recommend them. Okay, so I have some goals in here. One of the things I wanted to, I was just thinking about what you might want to take away from this. Understand the landscape of the HPC. I think we got a lot of that, and I'll maybe brush on a few things that Thomas didn't. Has anybody used the IPython notebook? Yeah, so some folks. I mean, I think that's keeping Python relevant, and I think as the years go by, it will be more and more where we interact with the web browser and have powerful computers behind. So I'm going to demo a few examples there. You can download them if they're super. Yeah, I guess just high performance computing, we're talking about solving big problems or solving problems faster. And I'm going to just kind of breeze through a little bit of this. That's our InfiniBand network. When you asked how agile things were, I thought about changing those tables. So here's, I mean, they're so heavy, they're breaking. Here's sort of the traditional parallel computing paradigm. You have C, Fortran, C++, and you link it with MPI, OpenMP. We have some accelerator technologies like CUDA and ACC now. Or you might do something in hybrid. And that's kind of been the standard, and we have a fair bit of that at CU. There's also sort of these newer technologies that people are running on supercomputers like MapReduce and sort of new message broker. I'm not even sure if that's the right technology or the term, but things like ZeroMQ and AMQP, which were developed in a different industry. And I think the point is they solve a different problem and they offer a different set of characteristics for users. And here's a picture of sort of the landscape. This is sort of the number of tasks on the bottom, and the size of the data. And sort of the traditional HPC would be, I have a few jobs I want to run, and they use a lot of cores, but maybe the data is modest. And this could be, I'm not showing cores here, so the cores would be the z-axis, and that could be, huge. And then as you increase the number of tasks and keep the data size modest, you get into things where maybe people traditionally use Condor, or even just scheduled lots of jobs through a scheduler on the system. There's a few other things like Dagman and Swift and Falcon. This is not a comprehensive list, just to give you an idea. And then the idea is, as you take that single task and you add a lot of data, you get to things like MapReduce. And if you kind of take that and, or either way shift somehow in the upper right corner, you get some tools like Pig and Hive, which I'm not familiar with. And I think this group probably has more set up. But I guess the idea is you're running lots of tasks with lots of data. So the stuff I'm going to talk about today really is over in this category. And it's the things that we've found our users run into most, or at least the users need help the most. So the difference, so many task computing was coined by, I guess, some researchers, Ian Foster and some of his grad students at the University of Chicago. And they just want to make a distinction between high throughput computing. This traditional high throughput is, I have 1,000 independent jobs, and I can just schedule them with something like Condor, and they can kind of get run over a period of months, and eventually get my data. And they made the point that you might have a lot of independent jobs, but you still want the performance you'd get if you were running an MPI job, where you'd say, oh, I'm getting a certain megaflops per second. You're trying to use a large resource in a short period of time. And so I think that's one of the big distinctions. And he even says applications that are not that are communication intensive, but not easily expressed in MPI. I think that's partly true, and then also, even if they are naturally expressed in MPI, maybe MPI doesn't offer the right characteristics, and that's what we've found. Yeah?
Would this be something where you also really care about the latency of being able to
Yes.
get that task scheduled?
Yeah.
Could you repeat the question?
Yeah, so that's a great question. I actually don't know if I can address that. So the question is, you have all these tasks, and do you care about the latency of scheduling that task? And you do for sure, because if it takes longer to schedule the task, the overall, you're kind of concerned with the overall performance of getting all of the tasks done. And things like, our scheduler, for example, if you submit a job to our scheduler, and then you submit another job, there's probably a minute or so that everybody gets no matter what the job is, because we have to run some tests afterwards to make sure the node's still healthy, and then it has to go to the scheduler, and that takes time. So really the trick is, for many task computing in this context, give me a big resource, and then you manage yourself. Yeah?
So you're going to talk about, related to that, is the overall end-to-end job flow in terms of how does the data associated with the job get associated with the job and delivered to the processor, as well as the state and binding of resources, especially if you need to checkpoint something so that it can continue later, or for fault tolerance, right, things need to.
Right.
Sorry.
So the simple answer is no. Yeah. So do you want to repeat the question?
Sure. So what I was asking is,
Is it on?
I think it's out of battery.
Out of battery?
I got an easy fix for that, Michael. I'm not gonna address it. It's a great. So basically, you're saying there's when you run a job or a set of jobs, you have to get the data from disk to the node, and then you have to fire up the job. And you may want to checkpoint the job along the way, and it could even be a bigger piece of a workflow where you have some dependencies between jobs, and you have to run certain jobs first. And the answer is, we're not doing that. We don't. I think we have a need for that, but we're not there yet.
Yeah, I mean, especially if multiple distinct jobs.
Yeah.
are interrelated because they're part of a workflow or something like that, then the resources that, phase one jobs worked on, then those have to be the nodes and resources that the phase two jobs need to run on.
Yeah.
Which means across your cluster, you now have a subset of qualified resources for nodes. Right?
Yeah.
So there's no cooperation, no synchronization process?
Well, there needs to be some notion of state, context, and binding. Right? So you can't just, because you have 1,000 nodes, you can't just run the job on any node that's available, because it's dependent on data and other associated jobs if it's part of a workflow.
So he's basically running all these processes in the company. Is that what you're saying?
Yeah, I mean, our problem is much more simple than
No
it's,
communication,
that's a-
cooperation, or synchronization.
yeah. We have, for example, we have users that say, oh, this could be anything from, I'm doing random number generation, so I need to do 1 million random numbers. There we go. Or we have users that say, I want to run, a few thousand MPI VAST jobs, and we just manage that. And they're totally independent, and for the most part, we just put them on the Scratch network and we go for it. So here's actually a good slide. We do have some folks using MPI and tightly coupled codes, and they're more from the traditional HPC background, and they don't need a lot of our help. The folks that are doing sort of, well, I just say non-traditional backgrounds, they're using languages like Python, and they don't want to learn C, MPI, and Fortran. And so Python's been a great fit for us. It links well to those other languages, and they're using it anyway. I just put kind of a list of things that sort of qualify as Monte Carlo simulations, parameter scans of search spaces. Uncertainty quantification qualifies as independent, and parameter optimization, doing some of that where we might use 100 or 200 cores per iteration. Okay, so Python for high performance computing. Here's just a quick list, a short list for you, of all the packages that I think are important that we're using. There's kind of a base set of packages you're probably familiar with. I wanted to point out, sort of in the HPC realm, MPI is great in terms of there's a handful of MPI packages. This one scales well. You could do multiprocessing and Python if you wanted to get some sort of like threading characteristic. And then PyCUDA and Numba has a package, or Anaconda has a package called Numba Pro that does bindings to CUDA. And we're going to have a tutorial next week if you're interested. I'll mention that. And then IPython, Parallel, and I would say that's one of the more important parallel packages we're using. I'll talk about that a little bit. Okay, so I'm going to skip over some of the success stories, but just to say that we've used a variety of these Python packages, and some of them to a large degree, and have some scaling numbers at the end that they'll be more interesting. Okay, so why is Python popular? I mean, I think if you use Python, you probably know, but I would say, if I just wanted to summarize it, two things. I'd say abstraction is pretty key. And then also, and I don't really have this up here directly, but a lot of people say, oh, I don't know Python, but when I see the code and you talk about it, I feel like I get it. And so it's a natural language, and it does a good job of extracting things. It's easy to learn, you can put things together, and it's got a great community. So here's an example I actually did kind of accidentally for our HPC class. Not accidentally, but I didn't realize it would scale so well. I was interested in writing a matrix multiply for them to test their matrix multiply again. So I took the Intel MKL, which is the math kernel library. It's very fast at that, and linked it up with HDF5 for reading in the matrices, and did that in C, and then just thought I would just compare it with Python just to see how fast it was. So I grabbed the Python PyTables package, which is the HDF5 interface, and compiled NumPy, which is the algebra or the linear algebra package for Python. And this is the code that this reads the HDF5 file, which is very simple, and so it reads in 2 matrices and then calls the MKL through NumPy. And so there's not a lot of code, and there's not a lot of places to mess this up. And here's how it compares. This is with C++ last week, and you can see the problem size goes up to the matrices. They're about 30 gigs each. I'm sorry, not 30 gigs each. They're about 6 gigs each, because we run out of space on the nodes. So we've got 3 6-gig matrices being multiplied, and this is the read and the multiply time, and it should do one right at the end. And so you can see that, in terms of performance, I probably need to run this more and get a real smooth number, but I can show you the C++ and HDF5 interfaces. The nice thing is you just don't want to learn that if you don't have to. So I think Python does a great job of pulling away those details and making it kind of easier and more fun, actually, for programming. Here's how many folks have done some MPI programming? A little bit? Maybe? Okay, yeah. So this slide may not be as meaningful, but let me just say this. I have a dictionary called data that has a couple keys and a variety of data types. And what I want to do is broadcast that to all my ranks in the system. And to do this in Python, it's pretty easy. I just say, grab the communicator, pass the data, and tell which rank it's coming from, which in this case is 0. And to do that in another language like C or Fortran, I would have to define a data type for this dictionary, and I have to figure out how to define the dictionary. And it's just quite difficult. And the performance of this may not be incredible, but it's also a very short amount of code. So again, a great example of abstraction. So I think we're ready to talk about many task computing. Hopefully you have an idea of what I'm talking about, at least in the context of CU, and then why Python is gaining some popularity. Here's some more Python code, and that's getting late. So this is just an example that I've whipped up that we'll use for a few demos. And so it doesn't do anything; it sleeps. So it's kind of like the FedEx version of many-task computing, right? There's no contention anywhere, which is nice. But it's just kind of a nice way to see if you're running lots of jobs, and when we're testing scaling, we just want to know if we run this on 1,000 cores, we run on 10,000 cores efficiently. So the question really is, if this is how I launch this, on the command line, a user might say, what's the best way to do this 1,000 times? As Thomas mentioned, we had some users submitting 5,000 jobs to the scheduler at the time. And scheduling is a hard enough problem when you have 100 things or 10,000 things, but when you start hitting more than that, it really is bringing our scheduler down, so we needed a different solution. And I think there's probably a lot of ways. You can probably sit there thinking like, if I had to run 1,000 different independent jobs, how would I do it in my favorite language? And you probably come up with a way. It's a quite common problem. So the Moab Slurm, those are schedulers. Those are kind of out when you're talking about jobs that might be really short, because that's inefficient, or when a user has a lot of jobs, or you're worried about the overall throughput. And then, and I would kind of put Condor in there too. It kind of comes back to the latency issue. The MPI for Pi is a great package, and one of the early load balancers we wrote was an MPI for Pi. And I have an example that just shows you it's not quite exactly what you want all the time. The scale is really low. And so on the Python side, there's see if you heard of Bldg job. It's one of them out there. I mean, if you go to parallel Python, you can see a whole page of different packages. The ones I put multiprocessing down just because if you just are using one node, and you just want to do something quick. It's easy to use. So I have an example of that. IPython parallel and celery, I did some scaling studies with, and I'll talk a little bit about that in a minute. So I think, yeah, so let's do, here's a bash example to run that same work job. And what you'd have to do if you wanted to run it in bash across many nodes is use a tool like pbsdsh. So that's kind of a bash-like tool that just says, run this command on all my resources. And the point really of this slide is just that this is a little bit painful. You don't want to have, say, hey, create a wrapper, and when you call it, you maybe pass in some dollar signs and whatnot. It's hard to really send it off, and it's a little bit inefficient. So this is a map of each box is a task, and I intentionally put a different distribution on each task so you can see that it's a little inefficient. If they were all took exactly the same amount of time, there'd be solid color on the screen, right? And that's what you want. So this is 20 cores, and I normalized it so that all these jobs start at 7. And you can just see that if you have a for loop and you run the jobs until they finish, and then you run the jobs until they finish, they have this inefficiency there. And so a much better schedule would be something that was static, in this case, where you could say, I'll divide the tasks up evenly among the workers, and then they do their work. Or even better would be something dynamic, which gives a little bit more efficiency, where you hand them out one at a time or hand them out 2 at a time. And then I thought this was interesting, Scoop, which is a Python package. It almost looks like they hand out a task, and then they do a little scheduling to see what the optimal balance would be if they could somehow measure the time. I mean, they can't do that, but it looks like they do that because they get a really tight schedule. And then finally, I think I'll come back to the fault tolerant example in a second. So one of the things that's different about IPython parallel or celery or things built with 0MQ or AMQP is they have sort of this broker model, and they don't necessarily have to, it doesn't have to be just one hub, but I just did this for a simple picture. So all the workers usually don't communicate directly with each other, they communicate through a hub. And so in MPI, it's no problem for me to send a message to another node, and that node to send a message to a node, and have this all-to-all communication if I want. Whereas with a message queue, if an engine sends a message to the hub and then dies, that message can persist. Whereas in MPI, one node goes down and they all kind of come down. So I think it's an example, yeah. So I have this bus. This is relevant. I guess one of the things that kind of got us away from MPI and into some of these other technologies is we had a scientist that had some code that reminded me of this Volkswagen. And that was, it's kind of what he was driving at the time, and it wasn't very reliable, but he wasn't ready to upgrade, and he just wants to use it. And so I tried to, when I started working with them, they had one application, and they would just submit jobs to the scheduler, and that application just wait for them all to get scheduled. And that was their sort of level of parallelism. And I remember talking to Thomas, I was like, oh, that's a slam dunk. We'll just MPI wrap that, and it'll be easy. And I tried to do that, and the Volkswagen would occasionally kill a node or something like that. And I just couldn't get the code to finish. And so it's actually at Python last year, I was chatting with the Python guys, and they were like, oh yeah, if you launch our engine with SSH, they can die and come and go. And it's sort of this elastic property that's pretty important. So I think it's time for a demo. I'm gonna go over and log into gems here. And hopefully not wait very long for a node. So right now I'm just waiting for hopefully 3 quick nodes. And I'm on a list of 4 nodes, so nobody else uses them, so there we go. So if you haven't launched, you can see that right? hit launch the notebook. And this wouldn't be the first notebook demo that failed for me today, so I'm going to use the backup if it doesn't work right away. It's an IPython package, and it's just notebook, and I like to include PyLab. So I launched the notebook. Oops, I actually need to go and do the correct. So you launch the notebook on Janus, and then once that's up and running, I need to create a tunnel. So I have a little script that grabs the node I'm on and creates a tunnel for me. And then I can should be able to reload this page. There we go. Okay, so it worked. At least it's working now. So I want to just point out multiprocessing. I don't know if I'll run this example. You can do it if you want to. It's just very easy to take something that you would normally use the map function with, and just create a quick pool of workers and map it in parallel. And it's included in the standard library, and you don't have to start engines up, and it's very simple. The one I wanted to point out was sort of the issue we had with some MPI. So I'm going to load just a few things here. This task is basically calling a little MPI complied dynamic scheduler on the work task. And I've got the standard MPI run command, except for I've added a couple please don't use the InfiniBand suggestions. And basically it's going to create 10 jobs per core, and they run from 1 to 2 seconds. So it should take about 15 seconds. So all this does is launches the MPI for me, and then reports when it's done. So right now it should take about 15 seconds. And the point here is I'm going to make one fail and just show you kind of the frustration you have if you were trying to just do something simple like load balance tasks with MPI. Okay, so there we go. We got, what did we get? We've got 36 cores, 360 tasks, and 16 seconds, which is about what we thought it would be. So now I'm going to do the same thing. I kicked up the runtime to 20 to 40 seconds, so I could pause for a second between filling some jobs. And then I just grab one of the children off of the master node that I'm on, because that's what I have access to. And there's the process IDs, and I can just kill one of these. And when I do that, I get this very familiar message that says, MPI is exited and your job is done. So I lose everything I've been working on, unless I wrote it to disk. And I guess what we've found is just not every code was meant to be run with MPI, and there's a lot of people that have code that you put a few different parameters in, and you don't know what's going to happen. And with Python, it's very easy to handle that situation. So here's a little IPython example. So you have to import a few things. Here's the work function that we looked at earlier. I'm creating 100 tasks with the same distribution that we just had. And if you want, you can kind of see, this is just, I'm just passing job times. And there's my array of job times. So I'm just going to load balance. Okay, I've got 360 actually. So on this expected duration of a single CPU per worker is about 20 seconds. And so let's start guide Python engines. And this is kind of idea called IP cluster start. They have a start tool in the notebook. Use that. And you can see if it started here. I've got 0 IPs. Got 11, so it's spinning up the engines while I wait. Now I've got all 36. So then I can create what they call a load balance view. I have 2 interfaces. One was specifically for this task. So I create the load balance view, and again, the kind of the key line here is I just use this map abstraction that I might use without, you know, if I didn't have Python, it would just be map my job times onto the work function, but instead I just call the load balance view. And again, this should take about 20 seconds. I should get in the habit of running those and then talking. I find myself with nothing to say while I wait.
Can you try plugging in the green gap?
This guy?
Yeah.
Oh, yeah. So 21 seconds. And we can actually look to see what that's like. I've got a little plot here that just takes the start and end times. Let's go back up to this function here. One of the things I return is just the start and end time for the job. So if you want to see kind of what that looks like, you can just create the graphic results, and you can see that does a great job of load balancing those tasks. So in terms of fault tolerance, I'm going to do the same thing. This little code snippet gets the engine IDs for IPython on the mobile board. And I'm just going to sort of do the same thing I did with MPI, where I just kill a node. And so I'm going to, again, load balance my jobs onto the work function. And then after 5 seconds, I'm just going to get rid of one of them. And instead of, I guess the magic here is it's running, and any second now I should kill a node, and nothing happens, right? So I've lost a node, and Python's like, you know what? It's fine. I can still map these to other tasks. And here I print out, you know, how many results I got back and the length of the jobs. So you'll see that those are the same. So even if a worker has a task it's working on and it goes down, the hub's smart enough to say, you know, oh, I'll reschedule that because I can hear back from you. You must have crashed. So it took 46 seconds, but I got all the tasks back. And if we look at sort of what happened, you can see here, this is the engine that died in the middle here. And it had to reschedule a task. And there's kind of a huge gap here, and I don't know why that's happening. I want to show you another example that's a little bit more realistic. Back here. Oops. Go to this fault line example. So here I actually created an example where the actual task would occasionally just fail, like 30% of the time. And so you can see there's some little white gaps where they failed and they had to retry. So it's a feature that IPython has. And then I think I killed three nodes here. I killed these two, and it actually still quite a bit more efficient than Bash, and not that much worse than if it just ran. So, so we liked IPython, and we just kind of thought, well, we should check to see how it scales, so that we're not recommending users do, you know, thousands and thousands of cores of something that won't run. And at the same time, how many people have used or heard of Celery, the task package? So I think it's kind of it's not for HPC. It uses AMQP, and that came from a different arena. And it's really popular as kind of a cron-like job, or it's for task management. But I thought it'd be interesting to just push that onto the supercomputer as well, and then sort of ask what recommendations we can give our users. So the weak scaling study we did was the FedEx task, basically, no contention on the file system, and we just want to know if this thing can manage the throughput of the jobs. And we just ran jobs from 27 to 33 seconds, and we ran 10 per core, so that's why it's a weak scaling study. and we ran up to all the cores we have in the system, roughly, not all of them, but about 12,000 of them. And so here's kind of what we found. This is just initialization time. So MPI, again, this is seconds. So we see that MPI is ready to go in 10 seconds with 12,000 cores. So when you call MPI init, it's pretty quick compared to Python packages. And Celery and IPython, we don't have to make a distinction, but it really was taking 100 or more seconds to start these engines up. So that would be an area where they could definitely improve. And I think part of it is they do a serial launch. So have one thing kind of launching these engines. And what they could do is, kind of fan it out, have launch to a node, a launcher, and that node launches something. That's much more efficient way to do it. And then here's kind of the results of kind of our test. We did an MPI static and dynamic schedule. So static where they all did the fair share up front, dynamic where they were kind of handed tasks as needed. So we did that for MPI and for IPython. And Celery just kind of has this dynamic scheduler, so we just use the default. And you can see that the IPython dynamic hits the wall pretty quickly. This is time in seconds. So it gets to about 100 cores and it starts to become quite a bit less efficient. The static can take it a little bit further, but then it kind of hits the wall. And then I think Celery sort of scaled the best of the non-MPI tests we had. And then the other way to look at it from our perspective is efficiency. And you can see, 50% efficiency here would mean that, if I'm using 200 cores with IPython parallel in this kind of a test, I'm really getting about half the efficiency out of the machine. Whereas if I could use something like MPI, I'd be much better off. Yeah, it's there. So here's kind of where we currently are at. Most of our users we pointed towards our MPI tool, and they just list their jobs in a file and it just load balances for them. And they're very happy with it, and it works most of the time. If for some reason their code needs something that's a little more fault tolerant, we push it towards IPython. We don't currently have anybody using Celery because the startup is it's not meant for a supercomputer, and so the scripts I had to write to actually get it to launch without kind of babysitting were not robust. They needed IPython. And if somebody's just using a single node and they just need a little boost, we push them towards multiprocessing. Partly because there's zero setup for that. They just need to add 4 lines of code. I think the sort of the downsides or the way places they can improve, certainly on the launching. It's a long time to wait for a job to launch. And then I think they do a good job of extracting the details of running at that scale, but I think they could use a little bit more abstraction still. So just to conclude, Python I think is a great way to manage these tasks. And I think Python, the community especially, has done a great job of creating packages that allow the users not to have to get into the details of some of the scientific computing packages, and they can just focus on getting their work done. IPython and Celery kind of bring to light this idea of elasticity, where you can have workers kind of come and go, and they can deal with that. And of course, I didn't mention memory and fault tolerance, but by memory, they almost do a checkpoint. So if your whole job did crash, and you had this feature turned on, you could kind of restart it and know which jobs you haven't finished. That's just kind of built in. You could do the same thing with MPI, it's just not out there as a package. And same with fault tolerance. You can catch faults of your code if they return some sort of error and retry them in IPython or in MPI, but you can't deal with an MPI. Yeah.
Let's say you checkpoint, change your code, restart the checkpoint.
I wouldn't say it's a checkpoint in the traditional sense. It's sort of a list of things you want it to do. So you might give it 1,000 jobs.
Could you repeat the question?
Sure. Yeah. The question was with the checkpoint, if you are running and then you stop for some reason and then change your code and restart what was the checkpoint for. It's a little more manual than I think a traditional checkpoint system is. And I'm the one that said checkpoint. It's not like on the website it's a checkpoint. It's just a database, and they just keep track of the jobs they finished. And so if your job crashes or you run out of wall time or something, and you decide you want to restart it from a place where it left off, and you change your code, that's totally fine. Because these are just yeah. It's not saving the state of each job; it's just saving the job that's finished. So one of the things I've been working on is an easier interface for our users, so they don't have to start the cluster in the JavaScript, and it tells them when it's ready, and then when it's done, it just shuts them down. So you can say something like with load balancer as LB, LB map, and when it's out of the with loop, it shuts it down and it starts it up, and that's been kind of helpful, and it does pull away some of the details. We're gonna next week. I'm presenting this to a conference we submitted to, and we do a series of tutorials in the fall and spring. So I mentioned this already, but next week, Mark Eversol from NVIDIA is going to give kind of a 3-hour Python CUDA tutorial. He's using the Anaconda package, which is pretty cool. And we'll also be doing some more of Python if you want to check out what we got. And if you want the slides, they're on GitHub, and the code is on GitHub if you saw examples of slides. And if you have any questions, you can as well. So, yeah, thank you. Yeah.
So any chance on having your meetups in the evening instead of afternoon?
Yeah, I think there's a chance. It started out as kind of, they're changing. It started out as a sort of a lunch club for CU folks, and our attendance was getting low, so we just kind of opened it up as a meetup, and it's gotten better. But yeah, I think more people would enjoy it. Yeah.
So, did you run the same benchmarks or tests? Did you run the same test in R? And I know R's got Python.
You're saying in R? Oh, like one of the R MPI packages?
Well, there's R parallel.
I didn't look at R yet. Yeah. It doesn't seem like there's as much. There's 2 R packages that I know. There's like Snow, and then there's MPI R, and there might be one more newer, but it doesn't have as many, as much support as Parallel. But I don't know anything about it. We have 2 or 3 people using Parallel R. Happily using Parallel R.
Do you guys have any people using Haskell or any kind of capability to use Haskell?
I think, yeah, you could use Haskell. If you can compile it, if you can download it, install it, you can use it. We don't have any Haskell users, but I know there's one student in our class that's he did compile some Haskell. I don't know if he was on Janus, he's not doing any research. So, I think it's a great idea, though. I would love to see more of our users use some of the emerging languages like Erlang and Haskell and Scala.
So are you guys running stuff? Are you guys running stuff on JVM as well? Do you allow that?
I don't know that we disallow it. I don't really know. So.
Any other questions? Lonnie, thank you so much. Dr. Hauser, Lonnie Lenachek, thank you so much. It's a wonderful overview of high performance computing and Python. Python language is amazing. It's growing every day. And I think within a couple of years it'll catch up to R in terms of its versatility. Thank you all for coming. We're going to head on over to the sink for some beers and for Cokes. Would love for you guys to come on over. and meet and talk with one another. And thank you again. Next month is in Denver, it's the University of Colorado Denver. It's going to be R plus Hadoop and a panel discussion on resolved traditional statistics is dead. Thank you for coming. Bye-bye.